Okay, good morning, everyone. So there's two announcements. The first announcement is, like as you recall in the course outline, there's a written test in week 5, okay? And the written test will be during your tutorial time. So either 10 o'clock in the Monday morning or Thursday 3 p.m. or Friday 1 p.m. It's up to your tutorial. So please go to your correct tutorials, okay? And then I have posted some sample test question in Moodle. If you go to assessment written test, you will see it. And then we will review those questions next Friday, okay? And so the test will cover everything from chapter 1 to chapter 3 inclusive. So everything up to linear systems. And it will last 50 minutes. And then you have to print a UNSW ID. So the first and the last time I check your ID, okay, for this class, and calculators, so approved calculators. So the calculators that doesn't have any programming capabilities. So you just do the multiplication, subtraction, simple, things like that. So exam booklets will be provided, so you don't have to print anything. Well, I think you can print some scratch papers, 1 or 2 pieces of scratch papers, but then no smartphones, no smartwatches, no laptops, no lecture notes. So it's like a simulated exam condition, okay? And then the second announcement is, many people ask me, when do we submit a lab, okay? So next week, the first submission will be next week. So you have plenty of time to do it, okay? So the first submission will be on Wednesday, and the second will be on Thursday. And then you have to do the problems, whenever you want to do it. But then for submission, then I will open a link in Moodle. Then you will see it, and the link will expire 1 hour after the lab finished. Suppose your lab finished at 1 o'clock, then the links expire after 2 o'clock, okay? You just upload through that. So you can work on the lab, you can work at home, whenever, whatever, but then you just need to submit via the link. And the link, question?
So we will also submit the week 4 lab for that? Or?
Week 4, yeah, next week, not this one. So this week I will upload the solution this afternoon. Okay? So the question for next week has been available, like for a long time already. So just have a look and do it, okay? And whether you do it or not, it was only 1%, okay? So do not be, question? No. So only in week 4, okay? Yes. Okay, so now we go back to the lectures. So last time we talked a little bit about, the condition number, and then, what is the consequence? So if you have a very ill-conditioned matrix, then the solution AX equal B might not give you accurate solution. And there is a way to fix that problem. And people call it a precondition of the matrix. And precondition of the matrix, you just multiply the left and the right by some matrix M. Yeah, and this matrix M will make the product, the condition number of the product MA will be smaller than the original matrix. So we are not going to go into details, but there's a way to fix that problem. So today we do another topic. What is the LU factorization? So you saw LU factorization briefly in the lab, okay? So what is the motivation? So the motivation that you can see from the lab yesterday or on Wednesday. So LU factorization offers you a faster way to solve the linear system when you have many linear systems at the same time, okay? So now maybe another example is, suppose you have a matrix, yeah, the same matrix, but then you have a lot of input vectors. Think your matrix like a black box, and the input vectors like the video stream, because like video stream on the internet, suppose you just, or voice over IP, Suppose you just break it down. It's just the vectors of 0 and 1, 0 and 1, you know, infinite length, yeah? And you just have like, so every second, then you have a new vectors, yeah? And every second you have to solve the linear system Ax equal B again and again. You know, a lot of filter and electrical engineering, you know, can be represented just by solving a linear system. Okay? So now, so what is the effective way to do it? And now you can see that there is a simple experiment. So if I go to MATLAB, yeah, so suppose I have like a million input, so 10 to the 6 is a million input, and then I just have one single matrix, okay? A is some matrix, and then I solve it again and again, you see? So B is like input vectors, yeah? And I just take a random 5 by 1 vectors. So just solve it again and again. So one way is you solve it by, you know, backslash operation, okay? And another way is you solve it by LU factorization. So LU factorization we will discuss, you know, in the next few slides. But the LU factorization, you just do it once, yeah? And then inside you just solve the linear system again and again. And now you will see that, now you run it. So you run it, you will see that there's a time difference between the two ways. So LU factorization is about 11 seconds. Sorry, the direct solver take about 11 seconds, yeah? But LU factorization is about 4 seconds. Okay, and you can make it, you see the first one is you just backslash solver, and the second one is LU factorization. So LU factorization is faster. Okay, and you can scale up and you see that, suppose I put like 10 million, you will see, you know, like there will be bigger difference. So anyway, so what is the motivation? So the motivation is you want to find a fast way, you know, to solve the linear system again and again when you have a lot of inputs, yeah? So that is the motivation. And now what is the LU factorization? So first, we define what is the lower triangular matrix. So lower triangular matrix is a matrix look like this. The off diagonals, yeah, upper part are just 0, and the lower part are non-zero, yeah. And if, you know, the diagonals, all the elements are 1s, then you got it unit lower triangular, okay. So you see, the name is very easy to remember, right? Lower triangular. So this one is lower, and this one is a triangle. Okay, and lower triangular part non-zero. And similarly, you can have, so what is a lower triangular matrix when you try to solve a linear system? So when you have a lower triangular matrix, then your linear system look like this. Okay? So it's the previous matrix, and suppose I have some values here, that I have this linear system. And you can see that when you try to solve this one, it's very easy. You got x1 equals something, then x2, you just, you know, get it out by putting x1 to the right, and so on. And this one, we call it a forward elimination. Yeah? And why the forward elimination is good? Because you can implement this one easily, right? I mean, think in terms of programming. So suppose you try to solve a lower triangular system like this. You can make a for loops, right? And for each for loops, for each iteration, you can just, you know, solve it easily, yeah? And now, in another direction, you can have upper triangular. So upper triangular, It's a matrix like this. Yeah, so the upper triangular part is non-zero, and the lower triangular, are zero, and diagonal is non-zero. Yeah, and if diagonal are ones, then you call it unit upper triangular. Okay, so it's a definition, so straightforward. And now, when you have a upper triangular linear system, you can use back substitution to solve it. Okay. So now, what is the LU factorization? So LU factorization is when you write A as a product of the matrix L, what is lower triangular, okay? And the diagonal are equal 1, multiplied by an upper triangular matrix. Yeah? So now the question is, what does it use for? Okay, now suppose that I know A equal L times U. Then instead of solving, AX equal B, yeah, I replace AX by LUX, okay, equal B. And LUX, you just combine UX to be the vector Y, yeah. So you do the solving in 2 steps. First, you solve Ly equal B first. Yeah. So you solve Ly equal B first by forward elimination, and then after that, you solve Ux equal Y. Yeah. So you solve into step, and in terms of computer programming, forward substitution, forward elimination, and back substitution are very easy to implement. Yeah, so once you have this LU factorization, then those 2 steps can be implemented easily. Okay. So now, I suppose this one is the matrix A. Yeah. So you can check that this matrix A can be written as a product of, like 2 matrices. One is the lower triangular and one is upper triangular. Okay? And then how do we solve it? So we can solve it by, so maybe why don't we just use MATLAB to do it, okay? So we have MATLAB, so we don't have to do it by hand. Okay, so before this finish, you see, so this one is direct solver is like 107 seconds, and LU factorization only 41. So it's like faster, still faster than than the direct solving. So now suppose I want to solve the I want to solve this problem, yeah? So this one is exactly the one in the lecture slide. So you have a matrix A given like this, okay? And so maybe I can draw like this, make it look like a matrix. Okay, and L is a lower triangular and U is the upper triangular. Okay, so now, suppose you have a vector B equals 4, 4, 7. Then you can solve in 2 ways. In 2 steps. First, you try to solve Ly equal B. Yeah, so this one is solving Ly equal B. And this one is solving Ux equal Y. Okay, so now we run it. So now you can see that the solution is just 101. Okay, so we have to check why we know that this one is the correct solution. Well, we just take A times X 447, and the vector B is 447. So just the solution, right? Question? I just made it up, right? Because here, 447 here. Yeah? Okay, so this one, instead of doing it by hand, I just use MATLAB to solve it. But I mean the same. Yeah, we're just lazy. Yeah. But now we have to check whether A equal L times U. So one way to check it is you just take A minus L times U, and it gives you a zero matrix. So A is the product of L times U, right? So now, how do you find the LU factorization? So believe it or not, you've been doing it for years without knowing it, okay? Because, when you study linear algebra, in first year linear algebra, when you try to solve a linear system, you have to do the Gaussian elimination, right? And actually, underneath the Gaussian elimination, actually what you are doing is you compute the LU factorization. Yeah? So this one is just an algorithm, but this algorithm just like for the computer. But for you, exactly what you've done in first year linear algebra is you compute the LU factorization. So let me illustrate by a simple example. So now suppose you have this matrix, yeah? So 103, 222, and 364. So how do you find the Gaussian elimination of this matrix? Let me So remember, this matrix is the one we just use MATLAB to compute, yeah? So you have 103, 222, 364, okay? Sorry. Yeah, so how do you do the Gaussian elimination? So you just take So you just take 103 here, and then you take row 2 minus 2 row 1, right? Yeah? So row 2 minus 2 row 1, then you have this one is 0, and this one is 2, and this one is 2 minus 6 is minus 4, yeah? And then you take row 3 minus 3 row 1, yeah? So then this one gives you 0, and this one gives you 6, and this one gives you 4 minus 9, so minus 5, yeah? Okay, so one step of the Gaussian elimination. So now you do the second step. The second step is you take you take row 2, you divide it by 1/2, right? So you take row 2, you divide it by 1/2. So you have 103, 0, 1 minus 2, 0, 6 minus 5, okay? And then the next step is you just take row 3 minus 6, row 2, right? So you got 103, and 0, 1 minus 2, and 0, so this one gives you 0, and minus 5 plus 12, is 7, yeah? And you see this one is the upper triangular matrix, okay? So if you go back to the previous slide, so you see this one is your original matrix, yeah? 103, 222, 364, right? And this one is your upper triangular matrix. So 103, 0, 2, so 103, yeah? So 0, 2 minus 4, well, just 1 minus 2, right? Yeah? So maybe we should not divide it, okay? So maybe we should not divide it, okay? So maybe we just skip 2 and 4. So we just skip this step, yeah? So this one is still 2 minus 4, yeah? So that means that you have to take row 3 minus 3 row 2, yeah? So just, okay, so my point is after the Gaussian elimination, you got the upper triangular matrix already, okay? So now, where do you get the lower triangular matrix? Where do you get the lower triangular matrix? So now you go back, yeah? So now you know that the lower triangular matrix is, so lower triangular matrix, yeah? You know that it has to be 0 here. So it should be 0, 0 here, yeah? And that's the unit triangular matrix. So it would be 1, 1, 1 here. Okay? So how about the entries? So the entries, so these entries, 2 and 1. So 2 and 1, it comes from, sorry, 1 is here already, but 2, where does it come from? So 2 come from here. So 2, actually it comes from the factor here. So it will be 2 here, okay? And 3, so 3 is come from this factor, yeah? So the factors that you use in your row operation actually are the entries for the matrix L. Okay? And then, sorry, can you see it? Yeah? And then number 3, so where's number 3 come from? So number 3 come from here. So this one. So give you number 3. Yeah? So essentially, when you are doing the Gaussian elimination, what you are doing is, in effect, you are computing the LU factorization. Okay? So now this is, if you look at this algorithm, it will be exactly here. So here, for every row k, yeah, so this is every row k. So row can run from 1 to n minus 1. Okay? Why is that? Because you don't, so actually this is row k plus 1 to row n, because you don't touch the first row, yeah? And now for each columns, then, first you compute the coefficient Lik, so by this ratio. So then, you compute the ratio when you do the Gaussian elimination. And here, so this one is just for every element from column k plus 1, you just adjust the values of the entries. So you're doing it like this. Actually, you're just, question. How do I know it? Well, because according, it's a bit like, there's a theory behind it, okay? But now, you just, if you look at this one, okay? If you look at this algorithm, there's no coefficient here. Here's 1. So that's why the diagonal is always equal 1. Question. So 2 and 3 here. and this 3 come from here. Yeah. Yeah, in that order, yes. Okay? So, but I mean, the details, we just skip the details. But what I want to say is, what you are doing, the Gaussian elimination, is actually you are doing the LU factorization question. Yes, because this algorithm, you see, here we have a minus here. So it means that here you have minus 2. So then, therefore, the LIK actually is the number 2. Okay? So row 2 plus 2, row 1, and row 3. Negative, yes. Yeah. Okay, question? That's your upper matrix, but your upper triangle matrix. Why it has a... You mean this one? This one? Well, because this is a calculation. Well, I mean, when we say that upper triangular, we just say that the lower part has to be 0. We don't say anything about the upper part. Upper part can be 0, can be non-zero. Yeah? So when we say lower triangular, then it means that we just say that the upper part has to be 0. So the 0 is important. And the other part, we don't care. It could be 0, it could be non-zero. Yeah? So any more question? Yeah?
How would interchanging rows enter?
A good question. So right now we don't interchange, okay? So just we will discuss the slide after, but it's a very good question, yeah? Okay, so, but you agree that, your Gaussian elimination, actually, it's just you are doing the LU factorization, okay, in your head. But now, this algorithm, will help MATLAB to do it for you. Yeah, so this algorithm. So now you can do the same for this matrix. Okay, 1, 1, 3, 2, 2, 2, 3, 6, 4. But you will see that this matrix does not have the LU factorization. Okay, so now let me try to do it. Okay, so quickly. So now, suppose I have. You see, in this case, you have the LU factorization for the matrix A. Okay? Now we try another example. So now I just try a very simple 1, 1, 3, 2, 2, 2, 3, 6, 4. Okay? So we change only one entry of the matrix. Remember before we have 1, 0, 3. And now become 1, 1, 3. Okay? And now let me do the row operation again. Can you see it? So let me do the row operation again. So I will do row 2 minus 2 row 1. Sorry. Row 2, yes. Row 2 minus 2 row 1. So row 2 minus, so 1, 1, 3 here. And row 2, so you got 0 here, 0 here. You got minus 4 here. And then row 3 minus 3 row 1. So you got 0 here and 6. No, sorry. So this one is 6 minus 3 is 3, yeah? And 4 minus 9 minus 5 again, okay? So now this one, you will stop here because, there's a 0 element here. You cannot go further. So unless you change the row, but now we don't allow you to change the row, right? In this algorithm, there's no step asking to change the row. So like you said, now we have to include the change in the rows, yeah? But now we have to go back, okay? So we just suppose that we don't change the row, yeah? Then what is the condition for which you have the row, you have the LU factorization? And the condition is, if you take the principal submatrix, yeah, and all the principal submatrix are non-singular, then you have the LU factorization. Okay, so what is the principal submatrix for this matrix? Then just have this matrix is order 1, yeah? Then A2 is just this submatrix, yeah? And then A3 is just a full matrix. Essentially, you just take the submatrix, which starts from the upper left corner, and you just expand it one step at a time, okay? So in this way, in this matrix, then A1 is okay, but A2 is a singular matrix, right? Because, you know, this row is a multiple of this row, so the determinant is just equal to 0. So this theorem says that, okay, if all the principal submatrix are non-singular, then you have the LU factorization. Yeah. So now we have this theorem, and we can say that this matrix doesn't have the LU factorization. And now we are talking about swapping the rows. So why don't you swap the rows? And that is exactly the next step. So I think we can skip this one, yeah? So you see, like swapping the rows is swapping the rows in terms of the Gaussian elimination. It's just like you have a pivot elements, right? So the pivot elements is you have everything below it are non-zero, yeah? And then if you don't have a pivot elements, then you have to swap the rows, okay? And now, so when you swap the rows, actually, you are multiply the matrix by a permutation matrix, okay? So now we have to modify the algorithm in order for the algorithm be able to swap the rows, okay? And in that sense, then you have to talk about permutation matrix. And now let me explain a bit more what does it mean by permutation matrix. So now suppose you have a matrix A like this, okay? So 103, 2, 2, 2, 3, 6, 4. And now suppose I want to swap two rows, yeah? So in paper, it's easy. You just write out another matrix, swap in the rows. Yeah, but in computers, you have to do something, and do something by matrix multiplication. And now I'm going to define a permutation matrix like this. So 0, 1, 0 like this, and then 1, 0, 0, and then 0, 0, 1. So look at this matrix. So if you take the identity matrix and you swap the first and the second row, then you have this matrix, okay? So every permutation of the rows of the identity, then they call it a permutation matrix. And now if I take P, I multiply A, then you see, in effect, it swaps the rows for you. It swaps row 1 and row 2 for you, okay? So swapping the rows in terms of matrix multiplication, you just multiply by a permutation matrix, yeah? And permutation matrix is you just take an identity matrix and you swap in the rows around, okay? And that is this step here. So here it says that the pivot elements, the pivot process is like when you interchange the rows. And it's equivalent to say that you multiply the matrix A by permutation matrix, then you apply the LU factorization. And it's always work, okay? You don't have to run into the problems before. So then instead of solving AX equal B, now you have to solve, you know, PAX equal PB, because now A equal LU, yeah? But LU is equal PA. Okay, and so you have PA, then on the right-hand side, you have to multiply P by B as well. You swap the rows for matrix A, then you have to swap the rows for the right-hand side, okay? And then you just solve it like as before. And, you know, I mean, this one, it just means that the first step, you don't solve Ly equal B, but you solve Ly equal PB. And after that, you solve ux equal y. So that's why you see that in the LU command in MATLAB, it gives you three matrices, the L, the U, and the P. Yeah, the P stands for the permutation matrix. This swapping the rows around. Because if you don't swap, then you can run into the problem that you might not have the LU factorization. Okay? So we can skip this one. So you can see that, suppose I have this matrix 1, 1, 3, 2, 2, 2, 3, 6, 4. So before I cannot do the Gaussian, I cannot do the LU factorization if I don't swap the rows. But now, if I swap the rows, then eventually I can get to the upper triangular matrix like this. Yeah? And the lower triangular matrix, you just record. So this one is 2/3, so that's why you have 2/3 here. And 1/3, so 1/3 come here. Yeah? And this one is this one is 1/2, so 1/2, so this one 1/2. And this is your upper triangular matrix. And you can check that when you multiply this L times U, then you get the matrix A, but row 1 and row 3 have been swapped. Question? Yes. You can do like that, but you can do either way, but you have to record what row you swap. Yeah, so this one, I swap it first, and then I can do the Gaussian elimination. But you can do it like along the way, and you see that you have to swap, then you have to record the swap. Yeah, but exactly that's what MATLAB is doing. Okay, and you see now I just said about the LU factorization. So it gives you three matrices: the L, the U, and the permutation matrix. Okay, and in this case, we just have the matrix 103 again, 2, 2, 2, and 3, 6 minus 3. And you see, if you do the pivot process, then this is the L matrix, and this is a U matrix. And the matrix P, so it record, then you swap the row 1 and row 3. You see, the matrix P, if you swap row 1 and row 3, you have identity matrix. Question?
Does P change ever, or is it always the same matrix?
Sorry?
Does P change, or is it always that matrix?
P can change. It depends on the matrix A. Sometimes you have to swap row 1 and row 3. Sometimes you have to swap row 1 and row 2. Sometimes you have to swap row 2 and row 3, and so on. So the matrix P recorded the swaps, and then it makes sure that PA has to be equal LU. Okay? Question? Like I said, like when it do the pivoting, then it will see, which row it need to swap. Okay, so in the next slide you will see it. So now in the next slide, so this one is, I think this one is one of the example. So in the lecture notes and in the slide, you can see that. Suppose this one is the original matrix, okay? Then, it doing the swap, and that record the swap here, okay? Then it doing another swap, and it record the swap here, okay? So eventually, you see this, this one will be computed along the way when it try to find the pivot elements, okay? So you don't have to worry about that. Question? Yeah. Just print out the final P. Yeah. Because you see, the final P gives you on the swap already. The final P, you just take the identity matrix, you swap it around, and just give you the final process, then you know that which swaps has occurred. Okay. So that is the example illustrate how it works. Yeah, in MATLAB. So roughly that is how it works, okay? And we don't have to implement the LU factorization again. Now we just use the command in MATLAB, but behind the scene, it just do the Gaussian elimination for you. And the partial pivoting, is swapping the rows to make sure that it can do further Gaussian elimination. And then record the swap for you in the permutation matrix, okay? And finally, what you need to know is just the matrix L, the matrix U, and the matrix P. And P times A has to be equal LU. Okay? So now there is another reason we need to swap, okay? So this one is another reason we need to swap the rows. So in this case, you just consider a very simple 2x2 linear system, okay? So here, mu is something very small number. And then you can compute the exact solution in this case, okay? And the condition number can be computed as well. Condition number here is just only 4. So the problem is well conditioned. However, when you try to use LU factorization, yeah, then, so what is that? So this one is the matrix A, yeah? So, and the matrix L, matrix U, and now you solve it. So X star will be your numerical solution from LU factorization. You solve it in 2 steps. And this is your exact solution, and you compute the relative errors. Okay, so relative errors are just the norm X star minus X over the norm X, and you run it. And then you see that the relative errors is quite big, like 0.07. It's like 7%. For a 2x2 system, you expect the relative errors have to be small, like 10 to the minus 5 or 10 to the minus 10. But this one, relative error is very big. Yeah? And now, why is that? Well, because so now the reason is because of the following theorem. But before we introduce the theorem, let's suppose that you swap the 2 rows. Okay, so you swap the 2 rows, then you run the system again. Okay, so now if I swap the 2 rows, so suppose I swap the 2 rows, yeah? So but I think if I swap the 2 rows, then I have to compute the LU factorization again. I did something. Anyway, I think if you swap the 2 rows, then the matrix L will change as well. So 1, the 1, 1, mu 1, and B equal 0, 1, like this, yeah? And the matrix, so matrix L will change as well. So 1, 0, and mu 1. 1, 0, and mu 1. So this matrix will change. So it will be 1, 0, and mu 1, 0, and mu 1. And the second one will be 1, 0, and mu 1. 1, 1, and 0, 1 minus mu. 1, 1, and 0, 1 minus mu. And now you run it again. See, you run it again, the relative error is equal to 0. Yeah? So you just swap. So what is the point here? When you swap the rows, you just improve the relative errors from, like 7% to 0. Yeah? So just a simple example, just 2 by 2 matrix. And the reason is because of this theorem. So this theorem just say that when you have the LU factorization, yeah, you introduce some errors to the matrix, okay? Then this is the one that you computed inside the machine, the L star and the U star, okay? Then, here, so this is the results here. Then the relative errors in the vector x is controlled by this quantity. So here the condition number, right, is still very small, okay? But this quantity can be very big. It depends on the matrix L and the matrix U, okay? So in our case, A infinity, the norm is about 4 or 5, yeah? But this number is like 1 over mu. And 1 over mu, when mu is like very small number, it's become very big. Yeah, so that's why the relative errors can be big as well. Okay? So this one, it's just another reason that you have to swap the rows. Okay, so just another reason we have to swap the rows in the LU factorization. Otherwise, you might run into this type of problems. Yeah? You see, so in our case, then the condition number is very small one, but the L infinity norm can be very big because 1 plus 1 over mu. And remember, we choose mu close to 0. So it can close up, yeah? So this product is 1 over 2 mu square, and mu is like 10 to the minus 15. So 1 over 2 mu square is 10 to the 30, yeah? So that's why, we have to introduce the pivoting process. So pivoting is just like you swap the rows, yeah? And you swap the rows, there's many ways to swap the rows, and partial pivoting, just make sure that the top guy has the largest in absolute values. Yeah, because there's many ways you can swap, right? And this partial pivoting, just make sure that the one on the top will have the magnitude larger than on the one below him. Okay, and that makes the swapping is unique in some sense. Yeah, you choose only the largest. And this one is the one that MATLAB is using. Yeah? And again, this one I just showed before. No? So this one is just an example. Suppose you have a 4 by 4 matrix. Then how you do step by step. So you see that the red one, actually the entries of the matrix L. Okay? So the red one, actually just the entries of matrix L. So you see, and eventually you got the matrix L exactly like this. Yeah, so the matrix, so this one is a matrix, matrix U, the upper half, and the lower half is just the matrix L. And why I use just one matrix to illustrate, like Anyway, so why I use only one matrix to store both? Well, because this one is exactly what MATLAB is doing. It doesn't create a new, empty matrix, but it's just storing the matrix L in the lower part of the original matrix. Just save some memory. Yeah. But actually, this one of two matrices at the same time. Okay. So the red and the black part eventually form a matrix U, and the green part is the matrix L. Yeah. And with the ones here. Okay. So with the ones are the units. So that is about LU factorization. Yeah. So any question? So you want to go on, or you want to take 5 minutes break? 5 minutes break, yeah? Okay. So we start again at 11:01. Okay?
So can we actually do the lab? Can we start the lab now? Or?
You can do whenever you want. But you cannot submit until next week. Yeah.
What if it's an infinite reversal?
So we just assume that the matrix is non-singular. Yeah. Well, because if you have the singular matrix, then I think the matrix L or matrix U might have 1 0 row. Yeah. And you will see that okay, then you have infinite matrices.
Well, I mean, something reduces the, like, when you put it in a triangle form,
Yeah.
it's just missing the single. If the
Yeah.
diagonal comes off, then that is infinite.
What happens?
So if that makes sense.
Yeah. When you have a diagonal at 0, then the determinant is 0. Yeah. No problem. Okay, so we start again, yeah. So remember in the beginning I ran the script. You know, one I used the direct solver, and one I used the LU factorization, and once the one that used LU factorization is faster. Okay, but we didn't explain why it's faster. Yeah, and now there is a way to measure two algorithms, which one is faster, and they do it by counting the number of operations. Okay, so floating operation. So floating point operation is, you know, one floating point operation can be either a plus or a multiply. Okay, so a plus could be a minus as well, right? Because b can be negative, yeah. Or multiply can be a divide. Yeah, so any operation that involves plus, minus, multiply, or divide, we just call it one floating operation. Okay, and the shortened acronym is just flops. You know, flop is for floating, and operation for OP for operation here. So one flop is just one operation like this. You know, either plus or minus, or multiply or divide. Yeah. So suppose that you compute the inner product, then, you know, you use about 2n flops, yeah, because, you know, you just take the products. How many products you have? N products, yeah. Then how many plus you need? N minus 1. Okay, so totally 2n minus 1. But when n is very big, we ignore the minus 1. Yeah, so it will be about 2n flops. Okay, 2n flops to compute the dot product of two vectors. And similarly, you know, I mean, you can count the number of operation of the LU factorization. Yeah, and the LU factorization, the number of flops is about 2n cubed over 3. Okay, so why is that? Well, because, you know, I mean, suppose you have a matrix n by n. So maybe suppose you have an n by n matrix like this. N by n matrix, yeah? So what you are doing for the Gaussian elimination now can be broken into a few steps. So initially, you know, I mean, you just fix this row, right? Yeah? And then you modify all the entries, I mean, here. So maybe 1, 2, 3, 4, 5, maybe another one, yeah? So this one is n equal 5, yeah? Yeah, so this is an n by n matrix. So initially you fix the row here, right? And you change all the elements, right? You have to change all the elements here. Yeah? And then after that, you have something like star, 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 and then you have 0, star, 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 star. So you have something like this after the first step. Okay? And then now you have to modify all the elements here. Right? Well, actually, you fix this row, yeah, and then you have to change all the elements here. So you have to change all the elements here. Then you get something like.
Sorry, your office.
Okay, sorry. But you get the idea, right? So now. You have something like this, yeah, and so on. So you have to do at least so. But you see the process. Yeah? The process is, at first you want to make this one 0. Right, and after that you make this one 0, and after that to make this one those are 0, and so on. Okay, so now we have to count the number of operations. So every stage, right, you have to compute the multipliers. So n minus 1. So you have to compute the multipliers to get out, the 0. To get out 0 here, so you have n minus 1 multipliers at each stage. Yeah, you need n minus 1 multipliers. And then at the second stage, so this one is the first stage, yeah? And second stage, you have n minus 2 multipliers. And so on. It keep reduced every stage, yeah? And then after that, you suppose you just go further and further, then, eventually you need to sum up, so at the last stage, then you have only 1 multipliers, yeah? So this one is like every stage you need to compute the multipliers before you can do the row operation. Yeah? So now I sum up, I say that, okay, so totally I have sum of k from 1 to n minus 1 for multipliers. Okay? And now, how about row operation? So now every stage I have to do some row operation to make, I make this one 0, then I have to modify those entries. Yeah? So how many operations do I need? So now, I have to, so at stage k, then I have a n minus k times n minus k blocks I need to modify. Okay? Okay, and then, so in each block, essentially, I have to do 1 addition, 1 multiplication, right? Yeah? So roughly, every block, then I have about, like k square operation. Yeah? So then, totally, I have the number of operations in each block is about sum of k square, and k run from 1 to n minus 1. And I mean, I can suppose I multiply and then add, so it could be 2 for each entries. Yeah. And then I just sum it up. So this one will be around, there's a formula for this. Well, I think there's an exact formula. So it will be 2 times 1 over 6 times n minus 1 times n times 2n minus 1 plus 1. Okay? So, but after you simplify this formula, it's about 2n cubed over 3 minus n squared plus n over 3. So we ignore, remember the big O notation. You just ignore the lower term, lower order. Okay? Then the significant terms is just this one. So 2n cubed over 3 flops. Okay? So that is how we have the two-thirds and cubed flops here for the LU factorization. Okay, and we say that the cost for computer LU factorization is of order O n cubed. So the big O notation, we introduced it before. Yeah? The big O notation is you ignore the constant, you ignore the lower terms. Yeah. Then what is the highest power? So essentially, for LU factorization, is about O n cubed operation. Yeah. And now, how about solving the, backward substitution or forward elimination? So remember, suppose you go back to the system, yeah? So suppose you have like x1, well, go back to the lower triangular system like this. So in the lower triangular system, so suppose a forward elimination. So how many operations do you need? So here to compute x1, you need one operation, right? So x1, so one operation. Yeah, you don't need to do anything. So for x2, how many operations do you need? Well, you need about like, so here, one operation for plus here, and one for multiplication. So it's about 2 operations, yeah? And for x3, so how many operations? So you could have like one operation here, one here, so it's about 3, yeah? And so on. So suppose you're up to xn, could be about n operation. N flops, yeah, so n flops. Okay? So then the number of flops, when you sum it up, it will be sum of k from 1 to n. And this one is about n square, yeah? So n plus 1 over 2, yeah? So it's about O n square operation for forward elimination, yeah? So you see, you counted the number of flops you used to compute, yeah? And now you can do the same for back substitution, yeah? Because it's the upper triangular, so you have a similar about O n square as well. So now we go back to the cost of the LU factorization. You see, so now solving well, because you see this one is because we have Ly equal B, you have n square, right? and then u x equal y, you have about n squared, so totally about 2n squared. But we ignore the constant, then it's about O(n) squared. Yeah? So now we just look at this one. So this LU factorization is about O(n) cubed. And then solving the triangular system is about O(n) squared. So when n is very big, n is like 1,000,000, then definitely LU factorization takes more time, right? 1,000,000 cubed is bigger than 1,000,000 squared. Yeah? And so now if you go back to the program, you go back to the MATLAB program, yeah, you will see that, because the LU factorization is expensive, we just compute it only once, yeah? And now inside, you just solve the linear system, I mean the upper triangular or lower triangular linear system by forward substitution or back forward elimination or back substitution, right? So that's about O(n) squared. So then, the cost is about O(n) cubed plus O(n) squared multiplied by n. N is the number of time you solve the linear system. Yeah? And now, if you try a direct solver like this, yeah, then the direct solver actually is just doing Gaussian elimination again and again. And you've seen that Gaussian elimination is the same cost as the LU factorization. It's about n cubed. Yeah, so in this case, it just get n cubed again and again. So the total cost is about capital N times n cubed. Yeah, so in this approach, it's only about O(n) cubed, but then capital N got multiplied by n squared. And you see that, for n very big, definitely this one will be smaller than this one. Okay, we've tried it, and you can see that this one will be bigger. So that is, why using the LU factorization will give you a faster algorithm. And you can see it before you run the program. You run the program, but now you can explain it just by counting the number of operations. Okay? And now this one is just a program. You can run it to check that, the time is about O(n) cubed. So I just skip this one. You can run it. So this one is compute the LU factorization, and then, compute the time, and then you just. So now I explain a bit more about this formula. So what does it mean here? So here is, in this program, it just doesn't know that the time is to some power, right? So it just take the time, yeah? And it assume it's a power of p. So we assume that is a power of p, n to the p, sorry. So how do you find p? Well, so now suppose you have time, so maybe this one time, yeah? So T for TLU, okay? So TLU. So TLUN. So I assume that TLUN is some constant n to the p, okay? And how do you find the constant p? Well, suppose you have TLU n plus 1. Yeah? Well, because n, so maybe not n plus 1, but suppose this one is n1, yeah? Because you can see that n any from this array, and this array just got. So what's the problem? So this array it just skipped by 10, yeah, and then just got multiplied by 500. So actually it starts from 500, and then 5,000, and so on. So we can have n1 equals c n1p, yeah, and then we can have the LU at n2 equals c n2p. Okay, so two values. So how do we find p? Well, we just take the ratio. So if you take the ratio, then the constant go away, yeah? You just have n1p over n2p, okay? And after that, you take the logarithm. So if you take the logarithm, TLU n1, TLU n2, then you just have p logarithm of n1 over n2. Okay? And anyway, so this formula is exactly this formula. Question? So TLU, if you look at this, will be the time that you compute the LU factorization. So you see this one, I just explained the formula inside the program. Okay? So TLUK is the time to compute the LU factorization because it equals finish minus start, and finish is like you take the CPU clock after you compute the LU factorization. Yeah? So TLUK. So here we don't know what is the power of P. We just assume that it will be, you know, the TLU will be some constant time the value of n multiplied by the power, raised to the power of P. And we try to find the power of P based on the real time, not based on the theory. Okay, so based on the real time. And the formula of P, the way to find P is just this formula. And I just explained why we get this formula. Okay, we assume that it's a constant time n to the P, and you just get the P just a logarithm, of this divided by logarithm of this. Okay, because it's n equation k, it's just this one, yeah. So n equation k is n, yeah. Okay, so this one is, the script to compute the n to the p. We compute what is the real p. Okay, the theory say that p should equal 3, yeah. But then we have to check whether the theory is correct. Okay, and this one is to check whether the theory is correct or not. And now you run it, then you can get the exponent is not close, not exactly 3, but it's close to 3. Yeah, so say n run from 500, 1,000, 1,500, and so on. And you can measure the seconds and you compute the exponent. Okay? So not exactly 3. So the theory say that it has to be 3. Yeah, but in practice, there is some overhead computation as well. So slow down a bit. So it's not exactly 3, but it's like 2.8 or something. Question? Good question. So what works for only square matrices? Well, usually for a linear system, right? When you try to solve it, then you should have number of variables equal to number of equations. Yeah. Otherwise, if you have an overdetermined, then you have to use least square. You don't use the linear system to solve it. Because we just consider the simple case. But if you have a rectangular matrix, we cannot solve the linear system. You have to solve a least square problem. Yeah. And it's outside the scope. You can do it maybe in statistics, but we don't have time here. Yeah? But it's a good question. Yeah. So here we just consider a simple case. When you have a square matrix, and you try to solve a linear system, then you use LU factorization. Okay. And LU factorization, it just comes from the Gaussian elimination. And you see, when you have overdetermined or like underdetermined, you cannot use Gaussian elimination anyway, right? Yeah. Okay, so now we move to the last topic of linear system, which is like, whether we have any faster way to do it. And yes, there's a faster way than LU factorization, but you have to require more on the matrix, okay? And now we introduce that matrix is symmetric positive definite matrix. And you've seen symmetric matrix already, right? So if it, if you reflect over the diagonals and you get still the same, then it's a symmetric matrix. But what is a positive definite matrix? So anyone taken linear algebra? 2601, or maybe you've seen this one in, did you see this one in first year? No? So positive definite matrix is just a matrix that, if you take any vector x, any vector x, you take transpose and multiply with that matrix. Then you multiply x again. Then you get a positive number. So anyone give me a simple example of a positive definite matrix? Yes, very good. So identity is a positive definite matrix, yeah? Because if you take any x, if you take any vector x, yeah, and you multiply, the transpose and on the left and the matrix on the right, sorry, then this one just gives you x1 square plus x2 square, which is always positive for non-zero vectors, right? So any other example? Any other example? Yeah? Any? Positive entries, you mean on the diagonal? But how about off diagonal? But it's a good point. If you have any positive entries, yeah? So if you have positive entries like this, then you have another positive definite matrix. So A, B positive, yeah? But you get the point, right? So here, it's just a special matrix. But there should be a cases when you have some number here non-zero as well. It's still okay, yeah? So that is a positive definite matrix. And here, I give you an example, what is more, non-trivial, So you have like positive and negative entries, yeah? But it's symmetric, so I have -1 here, -1 here. And then when you expand it out, okay? So this one is just a lengthy computation, and then you complete the square. And that's a sum of 4 square like this, yeah? And it's still positive when you have a non-zero vector. So it could be a complicated like this. It's still positive definite matrix, okay? So there's many ways to check, whether a matrix positive definite or not. And so one way is to check the determinant of all the principal matrix, yeah? So principal matrix, remember you just take the top left corner and you expand it out. Initially you have 1 by 1 or 2 by 2 or the full matrix. You check the determinant, okay? And if all of them are positive, then the matrix positive definite. And the second way is you check the eigenvalues. Yeah, so this one is also from linear algebra. I'm not going to prove it, but Actually, we can prove it. So why if the eigenvalue is positive, then why the matrix is definite? So can you prove that if the eigenvalue is positive, then the matrix is positive definite? Well, maybe I just leave it exercise, yeah. So no, it doesn't link to a determinant. I think it's something like yeah. Suppose you have an eigenvalues. Yeah. Suppose you have an eigenvalues positive. You have AV equal lambda V. Yeah. And then lambda is positive. Yeah. Then at least you know that V transpose AV will be lambda V transpose A. No, sorry. So it will be lambda V times V transpose, yeah? So it will be lambda V norm. So it's positive. So at least you know that for the eigenvectors. You know, if it positive eigenvalues, then this product V transpose AV will be positive, yeah? Because this one is square, yeah? And then I think every other vectors, you just expand as a linear combination of the eigenvectors. And you can use this property. But anyway, so this from linear algebra, we just skip it, okay? So, but you can check if all the eigenvalues are positive, the matrix positive definite. So now our main concern is the Cholesky factorization, okay? So Cholesky factorization is if you write a matrix as a product of, you know, upper triangular matrix, yeah? Take the transpose, multiply with that upper triangular matrix itself. Then we call it a Cholesky factorization, okay? So you see, this one is upper triangular, this one is a lower triangular, but they are the same. So this is a special case of the LU factorization, right? Because in LU factorization, you have a lower and the upper, but the lower and the upper could be non-related. Yeah, but in this case, the lower and the upper, actually they're just transpose of each other, right? So R is the upper triangular, and this lower part is just a transpose of the matrix R, okay? And for example, suppose I take this matrix, okay? You can show that if I take the matrix R to be like this, so this is the upper triangular, okay? And when you multiply R transpose with R, then you recover this original matrix. And this matrix, we showed before, is positively definite, right? So symmetric and positively definite. And in MATLAB, so we are not going into details how they compute it, but in MATLAB, there's a command, you know, you just enter the matrix A, then it will compute the matrix R for you. Okay, so CHOL, so stand for Cholesky, and Cholesky is the name of the mathematician who came up with this idea some times ago, maybe 100, 200, 300 years ago, I forgot, okay? So now what is the computation cost? So for LU factorization, you have 2 encrypt over 3, okay? But for Cholesky factorization, the computation cost is only 1/2 of that. Okay, so it's about encrypt over 3. And now you solve the linear system like before, right? So suppose you have, well, very similar to the LU factorization. So now suppose you have AX equal B. then you have R transpose Rx equal B, right? And now you let this one to be Y, so you solve RTY equal B first, and then you solve Rx equal Y. And this is a lower triangular, this is an upper triangular matrix, right? So you can use forward elimination or back substitution to solve it in a very quick way. So now, stability. So now, in terms of the relative errors, so if you use the LU factorization, then, well, I mean, if you use the Cholesky factorization, then the errors can be bounded by this inequality, okay? So epsilon is machine by epsilon, and this one is just a condition number. And rho n was given before, so rho n is rho n is this number, yeah? So rho n is about epsilon over 2, so about 10 to the minus 16, yeah? So essentially, the constant rho n is no, sorry, rho n is a constant not larger than 3n. So it means that rho n is about 3n, okay? So, or even smaller. So rho n can be very much smaller than n when n is large. So the main idea is the relative errors when you use the Cholesky factorization is just depend on the condition number. Okay? I mean, this one can be very small, this one can be very small. So everything just depends on condition number. So the condition number is very important in terms of the relative errors of the linear system when you try to compute it using the computer. Okay? So any question about linear system? I mean, that is everything about linear system. Any question? I want to mention one tiny thing here. So here, you know, I mean, remember this theorem is about if and only if. Yeah. So it's meant that two ways. Yeah? So if it's positive, symmetric, positive definite, then it has a Cholesky factorization. And vice versa. If it has a Cholesky factorization, then it is symmetric and positive definite. Okay? So one way is easy and another way is not so easy. So I show you the easy way, yeah? I mean the direction. One direction is not so easy. So the non-easy direction is suppose symmetric, positive definite. Then it has a Cholesky factorization. Okay? So it's not easy. You have to come up with an algorithm to do it. So there's an algorithm and people have done it. Okay? But the other direction is relatively easy. I can show you how to get it. So suppose, so see the theorem say that, you know, asymmetric and positive definite is equivalent to say that A has a Cholesky factorization. Okay, R is upper triangular and all the diagonal entries are positive. Okay? So now, this way I can show you easily, yeah? So suppose A equal R transpose R. Then you can show that A transpose, yeah, will be just R transpose R and everything transpose. And this one become R transpose transpose, where it's just R transpose R. So where it's just equal A again, okay? So I just say that A transpose equal A. So it's means that A is symmetric. Yeah. And another property is positive definite. Okay, so now if I take X transpose AX, so this one is a definition of the positive definite, then this one is just equal X transpose R transpose R and X. Yeah. And you know, you can rewrite this one as Rx transpose times Rx, and this one is just a norm of, the two norm of Rx squared. Yeah. And you know, this one is positive when X non-zero, right? I mean, if you have a non-zero vectors, remember this one is just a norm square. A norm square, then head on Y is positive, right? And when Rx equals 0, then because the matrix R is upper triangular and all the diagonal entries are positive, so it's invertible. You know, because if you remember the upper triangular, you can complete the determinant by taking the products of all the diagonal elements, so it's non-singular. So therefore, Rx equals 0 just implies X equals 0. Okay, so this one, just say that this matrix positive definite, so A is positive definite. Yeah, so at least I show you one direction, which is easy. Yeah, so this means that if you have the Cholesky factorization, then the matrix is positive definite by this argument. Okay? Yeah? Okay, so we have 15 more minutes, so I have to move to a new topic, sorry, because we are a bit behind the syllabus. This is the first time I'm doing the 10-year syllabus. 10-week syllabus, okay? So, we don't have a lot of time, so. Let me try to introduce a new topic. So I think I can take this one off, yeah? Okay? So now we move to a new topic, and the new topic is interpolation. So this topic will not be in the test, however, it will be in the final exam, okay? So everything up to chapter 4, up to linear system is on the midterm test, yeah? And everything from the beginning to the end will be in the final question. The final written, yeah. So you have only the lab test in week 7, I think 7, yeah. It will be in the computer lab.
That's the only computer.
Yes, that and the project as well. There's a project as well, yeah. But then the final exam will be written, so it's a conventional exam, yeah. Okay, so now I just want to have some demonstration. So suppose, like in some graphic models, you want to model, like some object, suppose I just take my hand, yeah? Then first you have to record the shape of the hands into the computer somehow, right? And this is one simple way to do it. Suppose I just put my hand here, then I just use the mouse to click, on the boundary of my hand. Yeah, you don't see my hand now, but you see the mouse is clicking, yeah? And you have seen this one maybe in other application as well, maybe some, animation program or anyway, so I'm just moving the mouse, yeah, on the plane, and then I just trace through the boundary of my hand, and then, I just trace it, and then I just connect the dot. So now I just connect the dot, okay? So it looks like my hand, yeah. roughly. But you see, that is exactly what people are doing in animation, they just have characters, like human being, and they measure on the coordinates in the 3D coordinates, and then they put in the computers, and then they will, make some transformation, make the object moving, and then make the animation. Okay. So now the question is, how do you find the curve? You see, I just click on the blue dots, yeah. And the MATLAB program just plot the red curve. Yeah? And this process, we call it interpolation. Okay, so this is interpolation. And now, that is the topic of the new chapter. So sorry, I have to go back here. So now we introduce a bit more formal, what does it mean by interpolation? So the formal definition is like this. Suppose you have a collection of points, x and y, on the plane. Okay, so in my case, I suppose I have n+1 points. Okay, then I try to find a curve, yeah, that goes through the points, yeah, and that curve, well, for the simplest case, I just assume that is a polynomial. Okay, the simplest one when people start with this problem, they just use polynomial. And the polynomials that interpolate the data, so the polynomial P, yeah? So it means that the red one is the polynomial, okay? The curve is the polynomials. And it goes through the blue points, so the blue points are the data point, xj and yj. And it has to go through all the n+1 points, yeah? Then I call it interpolation, yeah? So in this problem, we don't consider derivatives, so no derivatives. So just assume that the values are the same. So now, take a simple example. Suppose I have only 4 points, yeah? And then I want to find a cubic that goes through 4 points. So how do I do it? Solve a linear system, yeah? Okay, so one way is you solve a linear system, right? So what is very good? So suppose you have, so what do I mean by linear system? So now, so suppose you have a cubic P, it just equal A0 plus A1x plus A2x squared, right? So this one just a quadratic, yeah? So plus A3x cubed, right? And then now you have P0 equal 2. So it means that you have A0 plus, so 0 here, 0 here, 0 here, so plus on the 0 equal 2, yeah? So 1, 2, 3, okay? And now you have P1 equals 0. So then you have A0 plus A1 plus A2 plus A3 equals 0. And so on. So P2 equal minus 3. And then you have A0 plus 2A1 plus 4A2 plus 8A3 equal minus 3. And P3 equal 5. So you got A0 plus 3A1 plus 9A2 plus 27A3 equal 5. Yeah? So you got 4 equations, 4 unknowns, and you can solve it easily. You put into MATLAB, you solve it. Okay? But remember, you know, this problem was considered like 400 years ago. Yeah, and at that time, you know, they don't have computers, and solving linear system is not easy. You know, suppose here's 4 points, but suppose you have 100 points. Yeah, solving 100 by 100 linear system is not fun. Was not fun. Okay, and I think at that time, so Lagrange, he's a French man, he came up with a way not to solve any linear system, and you still get the interpolation polynomials. And the way you do it is you define, you know, a polynomial like this. So L1, so look at L1. So L1 is you just take, you know, x minus everything except the first point. Yeah, so the first point, remember, is 0. So x minus everything except the first point. And then the first point minus 1, 2, 3. Yeah, then you got these polynomials. So you can verify that. You know, I mean, if you put in 0, the first point, then you get 1. Okay? So you put 0 here, 0 here, 0 here, then everything just cancel each other, give you 1. And if you put other points, 1, 2, or 3, then definitely it equals 0. Okay? And similarly, you know, you can construct L2, L3, and L4. So L2 is like x minus everything except the second point. And then the second point minus everything. Okay? So you will see the formula after that. But then the L2 will satisfy it equal 1 at the second point and 0 at the other points. Okay? And similarly, L3 equal 1 at the third point but 0 at other points. And we can plot it. So L1 look like this. So L1 is the blue one, and it equal 1 here, but 0 here, 0, 0 at other points. 0 at all the data points, yeah? But at other points,